Right, so we're going to start out by looking at the first part of section 6.1. So with chapter 5, we pretty much ended what we're going to be doing with trig. With algebra. Now we're starting trig. Okay, before we start, I just kind of want to look at that word, break it down a little bit, and see if we can figure out what it means. So does anybody see in that word like either a prefix or a suffix? That sometimes you see that in other words. Yeah.
Try.
Try. Yeah. And I'm even going to extend it a little more, but try means what? 3. So try means 3. And how about gone? G-O-N. Think of other words in math that end in gone. Yeah?
Polygon.
Like polygon, octagon, hexagon. A gone is a sided shape. So trigon is the name of a shape. We normally don't call it that. What do you think we normally call a trigon? Yeah?
Go ahead and guess triangle.
It's a triangle. Yeah. So this means three-sided shape, which again we normally call it a triangle. But there is a name ending in gon for every shape. Pentagon, octagon, even a four-sided shape. You call it a quadrilateral most of the time, but there is a name ending in gon. Does anybody know the prefix? It's not a quadgon. It's a good guess because you think four-sided is quad. Yeah?
Would it be a quadrigon or a quatrigon, like with a T?
No, it's a totally different prefix.
Oh.
The prefix has to do with a game that was made a long time ago. Yeah?
A tetragon?
Tetragon. So in Tetris, all the shapes have 4 blocks to them. Tetragon is a 4-sided shape. We're talking about trigons. And then metry. Metry, you see that in various subjects like trigonometry, geometry. I guess that's really it. But chemistry. Not chemist. Yeah, not quite chemometry. But yeah, it was close.
I'm sorry, I just get dumb in this class.
So, metry means measurement. So, geometry, geo means earth, metry means measurement. So, one of the theories, although they can't really prove it, is that geometry was originally developed to measure things about the earth that you couldn't measure while you're on it. Like, how could we figure out how big it is? Well, before you could send a satellite and stuff into space, they had to try to figure it out. And that's the thought that was one of the original purposes of it. And now, obviously, it's a lot of other things. Trigonometry, triangle measurement. So pretty much every problem we do, especially word problems, is going to involve measuring something about a triangle. Maybe it's the sides, maybe it's the angles. And the reason you might do that is, let's just say you had like a tower over here, and you're standing right here, and you want to know how tall the tower is. And let's say it's cloudy. So sometimes you can use like a shadow proportion kind of method. But let's just say it's cloudy, so there's no shadows. But you have a device to figure out the angle to the top of that tower. Whether it's like a scope and you're looking through it, or you've got maybe a transit. If you've ever seen people like on the side of the road, like they have a tripod set up, and then down the road there's another tripod, and they're usually looking through. People know what I mean? You see those people?
Surveyors.
Yep, surveyors. They can use transits to measure angles and distances. So it's not actually that hard to measure the angle to something. So if you could get that angle, and maybe it's 30 degrees, and you know how far away you're standing, maybe it's 150 feet, what you've just done right there is created a triangle. Here's your triangle. And all you would have to do to find the height of the building is solve for x in the triangle. Find the height of the triangle. Now that is assuming, you have a nice tower that's perpendicular to the ground. That might not always be the case. You might have an object that's leaning. That's a little different. Okay? That would create a triangle that doesn't have a 90, a little harder. But still something we'll study eventually. So all that kinds of different things we're going to do in trig, a lot of it's going to come down to making some kind of triangle and working with it. So lots of triangles. So we're going to focus today on angles. Okay? How you can classify them, like if they're less than 90 or more than 90, how you measure them. And we're going to start out really basic with what is an angle made up of. Okay, so it's made up of two rays. The two rays have a common starting point. It's called a vertex. So that was a ray. And let's do one in a different color. There's another ray. Separate like that, they're just two rays. Make it so they have the same vertex, and now I just created an angle. So if you're going to draw an angle by itself, it's two rays. Now, when you make a triangle, like that, these are also considered angles, even though there's no rays in that picture at all. It's all line segments. So in a polygon where two line segments meet, we still call that an angle as well. But if you're going to draw an angle by itself, not part of anything else, you usually use rays. Alright, so when you draw it, you got two rays. One of the rays is the initial side, one is the terminal side. The way we figure out which side is which is you always rotate between the rays, the short way, in a counterclockwise direction. Where you end up is the terminal side. So if I go back up to my picture, it says for positive angles, we move in a counterclockwise direction to the terminal side. Right. So if I stay between the two rays and go counterclockwise, I go this way. I end up at the green side. That's my terminal. The side that I started at, the side in black, that's my initial. And I'm going to show you a couple more pictures of that. Initial, rotate counterclockwise between the rays to get to the terminal. Here's another picture. Now, I know when we look at that, we really have two angles. Right? There's an angle between the two rays, like inside of them, and then there's externally, there's another angle on the outside. Unless they specifically say in the directions, you're always looking at the angle between the two rays. So it's the angle that's less than 180, okay, the short way. Any questions on that? So when we have to solve for an angle that we don't know, a lot of times in trig they use a Greek letter to represent the angle. Just like X and Y are very common in algebra, well, these Greek letters are very common in trig. And we'll just name them going left to right. Does anybody know the name of the first one? Looks kind of like a fish. Kinda. Yeah?
Phi?
No. No, not that one. It's the first letter in the Greek alphabet.
Alpha.
Yep, and it's alpha. And then the next one looks kind of like a B, but one of the sides is a little longer. Yep.
Beta.
Beta. Yep. So beta. The next one, you might think it begins with C, right? A, B, but it doesn't. Anyone know this one? Yeah, Lucas?
Gamma.
That's gamma. Yep. This next one, the circle with a line going horizontally through the middle, that's a common one. That one's probably used the most when you have an angle you don't know. Yep.
Theta.
Theta. And then the last one looks kind of like a W, but the sides are a little curved and it actually loops on itself just barely in the middle. That's another Greek letter. Does anybody know that one? Yeah?
Is it omega?
It's omega. And that's a lowercase. If you're thinking, well, doesn't omega look like this? You might have seen that before. Well, yes, that's capital omega. My W looking thing is lowercase. If you do anything with like electronics or electrical, you talk about resistance, that's the symbol they use for it in ohms. But don't worry about that. The last one is omega. So we can make it easier to figure out which side is the initial side and which side is the terminal side if we just draw the angle in what's called standard position. There's two things that have to happen for an angle to be in standard position. The initial side is on the positive x-axis, and the terminal, vertex is at the origin. If you draw an angle and it meets those two criteria, then you have drawn an angle in standard position. So in red, there's an angle, let me make these rays. There's an angle in standard position. Just pretend like they're rays, one of them didn't stay on it. Now, if I move it like that, is that still standard position? No, what's wrong? The vertex isn't at the origin. The initial side is still on the positive x-axis, that's fine. But the vertex wasn't at the origin. All right, but if I did something like this? Why not? What's wrong with that? The initial side is not on the positive x-axis. The terminal side is on the positive y-axis. But the definition of standard position doesn't say anything about terminal side. Okay? So only one that I drew that is actually standard position was that one. Okay, so when we measure an angle, we usually measure it in degrees. All right, if when you're starting out, when you take calculus, degrees aren't really used. Okay, we use something else, which we're going to learn today. If you make one complete rotation counterclockwise, okay, so remember earlier I said something about rotating counterclockwise, that's a positive angle. So if you made one full counterclockwise revolution, how many degrees would that be? 360. So what if you did a half counterclockwise revolution? How much would that be? Yep, relatively. 180. How about a quarter counterclockwise revolution, Henry? 90. Right. So in all of these, counterclockwise, counterclockwise, counterclockwise. So let me draw some of these out so you can actually see it. Right. So there's your quarter revolution, okay, 90. If I go halfway, notice the top box says 180. If I went 3/4, we didn't do this one, but that's 270. And then all the way around is back at 360. But again, that was moving counterclockwise. So what do you think happens if I go in the clockwise direction? Yeah, Joe?
It's like negative 90?
Yeah, we get negative angles. Depending on how much you move, depends on what you get. But if you move in a clockwise direction, that's a negative angle. Okay, so we'll take a look at sketching some negative angles. So positive counterclockwise, negative clockwise. Okay, so you bring it back to 0. Now if I start going clockwise, look at my angle. Okay, it's negative. A lot of times though, all we care about is where we end up. So that angle that you're looking at right there, where this red dot is straight down, and this angle, where the red dot is also straight down, those two numbers are exactly the same number in terms of doing trig with them. Negative 90, positive 270, same number. So just to kind of show you, let's say I plug that into a calculator and I'm in degrees. Let's say I take the sine of negative 90. You don't have to worry about what that really is yet, but let's just say you do that, you get negative 1. Now I told you 270 is the same number, and it is. If you take the sine of 270, you get exactly the same answer. Okay, so when you're using negative 90 and 270 as arguments to a trig function, same thing. And there's a name for that, which I'll tell you in a little bit. Okay, so any questions on the difference between positive and negative? Now, what kind of angle do you think we would prefer to use if we can? Yep, Lucas?
Counterclockwise, positive.
Yeah, if we can, we want to stick with positive. So given the choice of saying, okay, I'm working with a negative 90 or positive 270, I'd rather you say it is positive 270. And there might be cases in word problems where the negative doesn't even make sense. Right? Maybe we're dealing with a triangle. Negative angles don't really exist in triangles. Right? But theoretically, they do exist if you just want to call it the other direction, okay, clockwise. So I told you there was a name for a negative 90 and 270, and those are a pair of what we call coterminal angles. Angles that are coterminal have the same initial and the same terminal sides. Same initial, same terminal. So let's go back and look at the negative 90 and 270 again. So there's 270. Initial side, positive x-axis. Terminal side goes straight down. There's negative 90. Exact same picture. Initial side, positive x-axis. Terminal side, straight down. Now, what we want to be able to do is convert a negative angle to a positive. I mean, I guess you could do positive to negative, but we usually do negative to positive. How can you get from negative 90 to positive 270 doing arithmetic? And if you watched what I just did, that's kind of a hint. Okay? Yeah, you can add 360 to get another angle that's coterminal. So 630 is another coterminal angle with negative 90 and 270. But that's kind of big. So this is like the opposite problem of a negative angle. It's getting too big. We'd rather make it smaller so you can subtract 360. So you can add or subtract 360 from any angle to get a coterminal angle. Get kind of the preference where you want to end up between 0 and 360. You don't want to be too big, you don't want to be too small. 0 to 360 is pretty good. Okay, so I'm going to ask you to sketch some angles and then find two angles that are coterminal with the one that I give you. One positive, one negative. Now, I'm not looking for you to use like a protractor and sketch this perfect. Okay, I'm looking for a rough sketch. So if you had to sketch like 90 degrees, I mean, it should look something like that. If you sketch 90 degrees and it looks like this, that's more like, I'd say 130, or it's much bigger than 90. Okay? So just a rough sketch. And it says to sketch them in standard position. So what does that mean? What do I have to do if I'm going to make sure my angles are in standard position? Joe?
Make sure that one of the lines is facing like straight right and it's on the Like center.
So it's going to start here and it's going to go straight to the right. That's my initial side. You can pretty much draw that for every picture we're going to do. Now 30 degrees. Well, if I went straight up with the terminal side, what angle would that be? 90. I want to go 30. So how much of 30 does that kind of take up relative to 90? It's like how much?
Like a third.
It's a third of it. So, if this was half, maybe about like that, you're going a little bit less than half. And so maybe about a third. So there's a 30-degree angle. Now I want to find two angles that are coterminal with 30. One positive, one negative. Can anyone give me or A, because there's an infinite amount, just give me a positive angle that's coterminal with 30. Yep, Rob.
390.
390, that's the first one you get. You just add 360 one time. But he could have said 750 or 1110. Any of these angles are coterminal. Just keep adding 360. All right, how about a negative angle? That's coterminal with 30. Lucas?
Negative 330.
Yep, negative 330. Questions on how we got those? Just add or subtract 360. That's it. All right, let's do 145. So there's my initial side. Can someone describe where the terminal side would be for 145? I mean, you could start with like a quadrant number and then kind of be a little more specific from there. Yep.
It'd be in, if the top right is quadrant 1, and it was like labeled counterclockwise, it'd be in quadrant 2.
Yeah, so a quadrant 2, upper left quadrant. Now, when I draw it, if I drew it straight left, it would be 180. Straight up would be 90. Is 145 closer to one of those two numbers or right in the middle?
Right in the middle. Not right in the middle. Close to 180.
Well, it's 55 degrees away from 90, but it's only 35 degrees away from 180. So it is a little closer to 180. 135 would be right in the middle. So if this is right in the middle, roughly, 145, maybe about like that. Okay. And if you want to put the arrow in, you can, just showing the direction you rotated. I could have done that up here as well. All right, and now we'll find two angles that are coterminal. Okay, what's a positive angle coterminal with 145? Lucas?
505.
505, yep. And how about a negative angle that's coterminal with 145? Yep.
Negative 115.
Negative how much?
Negative 215.
215, yeah. Okay, so there's 145 and negative 45. It's my initial. Where's my terminal side going to be now? Because it's a negative angle. Or I guess let's start with which way am I going to rotate to get to my terminal side? Yep.
Clockwise.
Yeah, I'm going to rotate clockwise. Now, 45 degrees, if you compare it to the x and the y axis, where would 45 degrees be? Robinson?
We're halfway now.
Halfway. So 45 degrees, the best you can. Sketch it halfway. Show the direction of rotation with that arrow. Now we'll do our coterminal angles. Positive, negative. Okay, what's an angle that's coterminal but positive with negative 45? Yeah. 315. And what about an angle that's coterminal but negative? About Sergio? Do you know what it would be?
405.
And because it's negative,
Negative 405.
you would just put a negative in front. Yep, good job. Okay, so any questions on finding coterminal angles? It's pretty straightforward. All right, so now we'll look at some different ways we can classify angles based on their size. Let's start with an acute angle. What does an angle have to be if it's acute? Yep.
Under 90 degrees.
How much?
Under 90.
Under 90, okay. I can think of an angle that's less than 90 that's not acute.
Positive.
And it has to be positive. All right, so acute angles have to be between 0 and 90. And that's an open interval. Cannot be either one of them. If it's 0, then the angle doesn't really exist, right? And then if it's 90, well, that's just another name for that. Okay, so acute angles between 0 and 90. A right angle, that's when your angle is how much? Exactly 90. So no range on that one, it's when it's exactly 90. And then we have angles that are bigger than 90 up to a certain point. Does anyone know the next category? These are angles bigger than 90, but they're also smaller than something. Yep. Obtuse.
Smaller than 180.
Yep. So obtuse angles are between 90 and 180. And does anyone know the name of an angle if it gets bigger than 180?
Big
A what?
angle. Big angle.
Big angle. Anyone have another guess? It's not a term you really hear a lot. It's called a reflex angle. Not sure if there's an upper limit on a reflex angle. I would think up to 360. Because then once you get beyond that, like 400, well now it depends on how you're looking at it. But I know a reflex angle is when it's bigger than 180. I'm not 100% sure if there's an upper limit on it. It's not really something you need to know. These are the three you need. Now the next definition, notice it says angles, plural. So now we're looking at two angles. And the two angles together meet some criteria. Does anybody know what the criteria is for complementary angles? Yeah?
Two angles add up to 90.
Add up to 90. Anything else besides the add up to 90? Like I could give you two numbers that add up to 90, but they wouldn't be acute complementary angles.
These have to be. You can go ahead.
Thank you, Henry. That's the acute.
They have to be acute, which means they have to be positive. So you could say it exactly the way Lucas said it. Two acute angles that add up to 90, two positive angles. That's fine. And when you study complementary, there's another type of angle you usually study right with it. Does anyone know the other category? It's two angles that if they don't add up to 90, it's supplementary. And what about supplementary angles? What's the condition for that? Yeah.
Two positive angles that add up to 180.
Two positive angles that add up to 180. Could you say two acute angles this time?
No.
No, because acute is less than 90. If you add up two numbers less than 90, you get something less than 180. So could you just say two obtuse angles then?
No.
No. Supplementary angles is always one of each. One acute, one obtuse.
2 right,
What's that?
2 right.
Yeah, yep, that's actually another case. Yeah, you could have 2 right angles. Yep. But you could not have 2 obtuse, you could not have 2 acute. You could have an obtuse and an acute, or 2 right. Negative angles do not have complements or supplements. So if I said, what's the complement to negative 15 degrees? There isn't one. Okay, so let's look at a few examples where I just give you an angle, and you tell me the complement, which means what do you add to it to get 90, and the supplement, what do you add to it to get 180. Okay, so the angle that I'm working with is 48 degrees. What's the complement of 48 degrees? Yep. 42. And what about the supplement? Yeah.
132.
132. Any questions on that? Okay, how about negative 18? What's the complement? Yeah.
There isn't one.
There isn't one. There is no complement. How about the supplement?
There isn't one.
There isn't one. So you could just write Na, or there isn't one, there's no solution, there isn't one. How about x degrees? And for this to work, you have to assume that x is a positive acute angle. X is not a negative number. Otherwise, you could just write no solution. Okay. So I'll write it this way. X is between 0 and 90. Yep.
90 minus x.
90 minus x. You're guaranteed if x is between 0 and 90, 90 minus x would never be a negative number, so that's fine. And if x is between 0 and 90, it would have a supplement. For example, if I gave you an angle of 170 and said, what's the supplement? Actually, no, you could still do that. It would be 10. So, yeah, I guess for the supplement, technically x could be from 0 up to 180, not including 180. But for the complement, it had to be 0 to 90. Yeah. Are you going to tell me the formula, the supplement you go? Yeah.
It's 180 minus x.
Yeah, it's 180 minus x. Again, as long as x is not over 180 and it's not negative. Okay, any questions on that one? Okay. So, another way we can measure an angle is in radians. So you might have seen as I was using this program, like, you see another number in the box below, like 10.19. That's radians. Okay. Now, as I drag it, what do you notice what happens every now and then to the radians? There's a pi in it. So it happened at 570. It happened again at 540. It's going to happen again. Various angles. 510. If I do it for smaller angles, you might see a pattern. So it happens at 30. Happens at 45. Happens at 60. It does it also at some of these weird angles. We're not going to talk about much, not with that today. Does it again at 90. If I can get it on 90. Anybody notice a pattern to when all of a sudden it changes to a pi? Yep.
They're all multiples of 15.
Yep. It doesn't, I don't think it'll do it for 75. There is a way to do it, but this calculator doesn't. So this calculator does it for anything that's a multiple of 30, 45, and then it does some weird halves in there. But it's mostly multiples of 30 and 45. And that's what we're going to kind of focus on. So, what I'm going to do is I'm going to start out by describing to you visually what a radian looks like. Eventually, we want to be able to convert between radians and degrees. Okay? But this is going to be more of a visual than a formula. Okay, the formula comes next. So what I've drawn here, that's a central angle. A central angle is just an angle drawn inside a circle where the vertex is at the center. So I could call that angle ACB. Ray CA and ray CB come out from the center of the circle, and at some point they hit the perimeter. Ray CB hits it here, ray CA hits it right there. If you connect, tracing along the path of the circle, from the two dots that I just put, that's an arc. That's called an intersected arc. And I've called it arc AB. You could also call it arc BA. Arcs are non-directional. Doesn't matter. All right. So now, if you were to take a piece of string, okay, and there's more sophisticated ways, but just to kind of keep it simple. If you took a piece of string, laid it on that arc, got the piece of string, and then straightened it out, put it on a ruler, you could measure the length of that arc. And then you could do, with the radius, it would be even simpler. You just take a ruler and measure the radius. If the length of this arc and that radius came out exactly the same, then you would be looking at a picture of 1 radian. Okay, in that picture, to me, I think the arc looks a little bigger than the radius, so that's probably a picture a little bigger than 1 radian. I might have had to put maybe the terminal side more like that. And then I think the arc and the radius would have been closer. Okay, but if the length of the arc and the length of the radius come out exactly the same in a picture, you are looking at a picture of 1 radian. Still doesn't really explain how to convert between radians and degrees. It's just kind of how you could visualize 1 radian. Any questions on that? Yeah.
So it's like 1 radian, like is that like a constant like value, or is it like specific to every circle?
No, it's a specific amount of degrees. Yeah, there is exactly a certain amount of degrees in 1 radian, and that's on every circle. It's always the same. Yep. And that's what we're going to kind of figure out next. So, converting between degrees and radians. Well, anytime you want to convert between two things, you have to have a starting point. Like, the example I used in the last class was converting between feet and inches. What's the conversion? If I wanted to change feet to inches or inches to feet? 12 what? In a foot. 12 inches in 1 foot. Now, he could have said that different ways. He said 12 inches in 1 foot. Could have said 24 inches in 2 feet. 36 inches in 3 feet. Okay, I didn't tell him how to say it. He said it. And he said it with a 1. So we're going to come back to that. But a lot of times when you give someone a conversion, putting a 1 in it is the easiest way to do it. Okay, 12 inches in a foot. 1 foot. Now, he gave me 2 very specific numbers, 12 and a 1. If I wanted to convert inches to feet or feet to inches, am I restricted on what numbers I can put here based on the 2 numbers that are on the other side? Yep.
Well, like, if you were gonna like convert something, you mean?
Yeah. Is there like any number that I would not be allowed to put in the top?
Oh, not the top, no.
Or the bottom?
Oh, I guess not the bottom either.
I mean, except 0. I wouldn't put 0 in the bottom anyway. But
Negative numbers.
and negative numbers wouldn't make sense for length. So sticking with the numbers that you're allowed to use, positive numbers, is there any restriction on what you put in for inches or feet? Yeah.
No, as long as they make sense with each other, different bold or one.
Yeah, I'm saying like if you just filled in one of them and left the other one blank.
Oh, then no.
then no. I could put in 80.3 inches, and I could figure out how many feet that is. Even though Joe gave me a 12 and a 1, it doesn't limit the two numbers I can put over here. It's just a starting point, the 12 and the 1. It's just like a fact that we all know, we all agree on, and we use it. Well, we kind of need a starting point here. A fact that we all know, we all agree on, and we use it. So I'm going to have to kind of give you the starting point because it's a little tricky to come up with. And the starting point, it's going to be based on what's called a unit circle. A unit circle is just a circle with a radius of 1. That's all it is. So it's a circle with a radius of 1. Now, just because I'm using this special circle with a radius of 1, it's not going to limit what I can convert for degrees and radians. Just like we use this special number of 12. It does not limit what you can convert between inches and feet. It was just a starting point. That's all it was. And that's all this is. It's just a starting point. 1 is just an easier starting point than some other numbers. Okay, so that's a unit circle. Now, the fact I'm going to give you that you probably don't know is that in a unit circle, something special happens. If you draw an angle in a unit circle, like that, let's say that this was 1 foot. Right? Let's say that you took a piece of string and you measured this, and it came out to 1.8 feet. Okay, you measured it, and you got 1.8 feet for the length of the piece of string right here. Well, if this arc is 1.8 feet, this angle would be 1.8 radians. In a unit circle, that always happens. The size of the arc and the size of the angle come out exactly the same. And that's what I'm writing right here. If you measure an angle in radians, it will come out equal to the length of the arc. So like I said, my arc, I just pretended it was 1.8 feet. The angle is 1.8 radians. If the arc was 2.6 feet, the angle would be 2.6 radians. So arc size and angle size are equal to each other on a unit circle. Knowing that fact will help us figure out a connection between degrees and radians. That's what we need. Once we know that this many radians equals this many degrees, that's like knowing this many inches equals this many feet. And then you're good. So what we have to figure out is we have to find an angle that's a common angle that if we drew it, we would already know how to find the length of the arc. Right? If you just pick some random angle and you try to find the length of the arc, we're not going to know how to do it yet. We've got to pick an angle that would make finding the length of the arc easy. A special angle. So that's what I'm saying right here. We've got to find an angle that would make finding the arc length super easy. It would almost be automatic. You could just look at it and already know a formula from geometry to find the length of the arc. Does anyone have a guess how big we could make the angle? And it would make the arc very easy to find. Yep, Robinson?
90.
Okay, let's start with 90 and let's just draw a picture of that. So if we make, let's go back here. So if we make the arc, we make the angle 90 degrees. Here. Here's your initial. Here's your terminal. There's your arc. What's special about that arc that it wouldn't be that hard to find its length? Yeah?
It's like, it's a quarter of the diameter, so like you know the diameter, you know the side of the arc.
It's a quarter of the what?
Circumference.
The circumference. So I think even easier than working with a quarter of a circumference, we could make it You can make it half. Here's your initial. Here's your terminal. And that's an arc that wouldn't be that hard to find because it's half. But in geometry, you learn a formula for an arc, but you usually don't learn the quarter arc or the half arc formula. You learn a formula for what? The whole thing. So now, if we put the initial side right there, put the terminal side right there, and let my arc be the whole thing. Now I've got an arc that's so big, we don't even call it an arc anymore. Lucas just said what we called it. It's a circumference. And we already know how to find that from geometry. So let's find the circumference of this circle. And why is that going to be important? Well, this fact right here. If you can find the circumference, or the arc, call it that, but it's the arc that goes all the way around the circle. If you can tell me how big that arc is, that's exactly how many radians there are to go all the way around a circle. Then we'll know 360 degrees equals this many radians. So let's see if we can figure out the size of the arc. This is a unit circle. Unit circle. What's special about a unit circle? Yeah. The radius is 1. So let's find the circumference of the unit circle. 2 pi. I'm just reminding you, if you didn't know the formula, it's circumference equals 2 pi r. So it's 2 pi times 1. So what's the circumference of the unit circle? 2 pi. 2 pi units, whatever that is. Feet, inches, doesn't matter. So the arc that goes all the way around is 2 pi. So what does that mean as far as how many radians to go all the way around? So what did we say about the arc in a unit circle and the angle in a unit circle? They are what? They're the same. In a unit circle, the angle is equal to the arc. Angle equals arc. Our arc is 2 pi. So what's our angle? Dominic? It's also 2 pi. So we just figured out how many radians to go all the way around the circle. The arc is 2 pi, and that's equal to the angle in radians, 2 pi. So now we know, based off that fact, that in 1 revolution, that's 2 pi radians. Or you could say 360 degrees. So there's your connection that's important. Now it's like you know feet and inches. You've got an equality between the two, except ours is radians and degrees. So if 2 pi radians equals 360, what would pi radians equal? How much? 180. Now, that's fine. You could give someone a conversion like that, but that's kind of like saying, you know, in 48 inches, there's 4 feet. It's true, but there's an easier way to say it. When you give someone a conversion, to make it easy, what number do you usually put in it somewhere? 1. So there's 2 ways to get a 1 in this formula. Let's get a 1 on the right side first. What could I do to both sides of this equation to get a 1 on the right side? Yeah. Divide by 180. Divide by 180. Divide by 180. Now I get 1 degree on the right equals pi over 180 radians. So now I have a formula for 1 degree. Let's say I wanted a formula for 2 degrees. what could I multiply each side by? I wouldn't have to change anything else. I could just multiply each side by what? To change that formula, 2 degrees equals something. Lucas?
Just multiply by 2.
Yeah, if you multiply, let's put what we're going to multiply by in this box. If you multiply by 2 and multiply by 2, now it says 2 degrees equals, and you have a calculation you can do out for radians. What if you wanted to know 6 degrees? What would you do to both sides of that equation to get a formula that says 6 degrees equals? Oh, Trish? Are you sure? Joe?
You just multiply by 6.
Just multiply by 6. Now you just created another new formula that says 6 degrees equals, and you've got a calculation you could do out and get the answer in radians. What do you notice as part of the calculation each time? The number in the red box changes, but what stays the same? And what else? The pi. The pi over 180 stays the same all the time. So if you want to convert degrees to radians, that's the calculation right there. You take whatever you have, you multiply by pi, and then divide by 180. So degrees to radians. Multiply by pi, divide by 180. That's the 2 steps. And it comes from, I tried to just explain where it came from. Yeah. Yeah. Okay, so that's degrees to radians. Now, when we did that, we got a 1 on the right side. Where else could I get a 1 besides the right? Oh, Henry?
Oh, sorry, Mr.
Not sure. Where else? What other place could I get a 1 in that equation besides the right? Joe? Put it on the left. So let's do the same thing again. Pi radians equals 180 degrees. Tyler, how could I get a 1 on the left? Divide by pi. Divide by pi. Divide by pi. Pi divided by pi gives me how much? 1. So now it says 1 radian equals, and now you're going to have a formula. If you want to know exactly how many degrees in a radian, do out this calculation. 180 divided by pi. 1 radian equals 180 divided by pi. Now, what if you wanted, let's say, a formula for 2 radians? What could you multiply each side by to change what's on the left to a 2?
2.
Yeah.
2.
Yeah. So now it says 2 radians equals, now you have a calculation you could do out. 2 times 180 divided by 360. What's going to stay the same each time is what's in red on the right-hand side. What's in the blue box will change. But if you want to convert from a radian to a degree, you multiply by 180 and you divide by pi. And I have that written right here. You multiply by 180 and you divide by pi. That's how to change radians to degrees. Now, they're very similar. One's multiply by 180, one's divide by 180. One's multiply by pi, one's divide by pi. So I'm going to show you a way you can remember which way is which without even having to memorize any of that. The only thing you have to remember is when I say 180, I want you to think, okay, 180, that's the number you think of with degrees. So just connect those two things in your head. 180 degrees. When you think radians, I want you to think pi. Radians, pi. Radians, pi. So if you just remember that, that's all you need to remember. 180 degrees. Pi, radians. Let's look at an example. So we're going to convert 30 degrees to radians. Now, I know it's either pi over 180 or it's 180 over pi. Every single problem. Pretend like 30 was a fraction. You've got degrees in the top. I'm trying to get to radians, so I want degrees to cancel out. In the fraction, I'm going to put in blue on the right. Where would degrees have to go to cancel out the degrees that's already there? Yep. Would have to go in the bottom, which would mean my other unit would have to go in the top. What's the number I said to always connect with radians? Pi. Pi always goes with radians. And what always goes with degrees? 180. So if you just think about where the unit would have to go to cancel, that pretty much sets it up for you. So degrees and degrees cancels. 30 goes into itself once. How many times does 30 go into 180? 6. So your answer is 1 times pi, or just pi, over 1 times 6. 6. And that's it. That's your answer. Now, what does it look like I might have forgotten to write, but I didn't? Anyone have a thought what I might have forgot, but I did not forget anything. I did not forget anything, no. That is a correct answer. That's how it should be written. Does anyone have a thought what some people might think should be there, but it's not there? Radians, the label radians. Radians is invisible. Okay, whenever you're talking about angles, if you don't put a label, everybody assumes it's radians. The only time you have to put a label is if you want someone to know it's in degrees. Then you put the little circle. But if you leave it blank, it's always radians. Right? So you got to kind of get used to not seeing RAD. You won't see it on the test. You won't really see it in the book either. Okay, let's try this one. So 45 degrees. All right, I think of degrees in the top. Sergio, if I want to cancel out degrees, where would it go in the blue fraction? It would go on the bottom. And what number do we always connect with degrees?
180.
180. And the other number is pi. Pretend RAD is written, but it's invisible. Degrees in the top, degrees in the bottom. Trish, what are both of these divisible by?
45.
Yeah, they're both divisible by 45. How many times does 45 go into 180?
4.
4. The answer is pi over 4 radians. If we go back to our circle for a second, 45 degrees. There it is right there, pi over 4. Notice, I'm not writing any of these as a decimal. I'm not pressing the pi button on my calculator and dividing by 4. The only time I would do that, let's do one. I kind of skipped ahead a little bit. You could just call this example, just put it under example 3. Just call it example C. This one, it's the same directions. Find the radian measure. So convert to radians, but round. Usually they're going to have you round when the angle is not a multiple of 30 or 45. But technically they could have you round whenever they want. Okay. Joe, what number goes in the top here?
Pi.
Pi. And what goes in the bottom? 180. Degrees. Degrees in the bottom, degrees in the top. Yes, I know I can reduce that. I'm not going to worry though, because I'm going to round it. So just type it all into the calculator. 500 times, make sure you use the pi button. which is second and then the caret, and then divide by 180. So that's about 8.73 radians. Okay, always use the pi button, don't use 3.14. Okay, and we'll finish up with, let's try 1 or 2 the other way. Convert that to degrees. If you want to pretend what I'm writing in blue there that's invisible, RAD is in the top. I want to change to degrees. So where would I put radians in the blue fraction to make it cancel? Yep, put it in the bottom. What's the number that we always connect with radians? Pi. The number we connect with degrees? 180. And now look what cancels out. Pi, pi. Radians, that's usually going to be invisible, so you're not going to cross that out. That cancels. 2, it doesn't cancel, but it reduces. And all I'm left with is 3 times 90, which is how much? 270. And that's how you convert back to degrees. The only one we didn't really do was converting to degrees and rounding as a rounding it. If you do this one and you do it with 3.14 and you do it with the pi button, you get very different answers. It's not like you get an answer that's only off by like 100th. You get an answer that's off by, I think, over 1/10. It's almost 2/10 off. That's not good. So when you round, always use the pi button. All right, so homework tonight, a little bit of everything we did, like classify an angle as acute or obtuse, find a complement, find a supplement, find a coterminal angle, and then some converting between degrees and radians. Some are convert and you leave it with pi. Some are convert and they're going to say round. If it doesn't say round, leave pi in the answer. Okay? So we'll go over that tomorrow, and then we'll take a look at the last part of section 6.1 tomorrow.